All right, we are back with the Xanadu Quantum Codebook, doing the same sort of, I don't know, improvisational or extemporaneous style in which I just go through these tasks and without looking at them, I actually have not looked at any of them. And so sort of showing how the problem solving techniques I use are done and such. So we're just picking up right where we left off with section I4, it looks like. So in this one, we're getting into some gate-based operations. Specifically, it looks like the X gate and the H gate. I don't know why it's X and H instead of just the poly XYZ, but that's what they have. So looking over here, we know that X gate is the bit flip gate. Hadamard puts it into equal superposition. It also changes the basis, basically, is what that could also be said to do. Change it from the Z basis to the, I did not even know this is called the Hadamard basis. I always just called it the X basis. I'd never heard it called the Hadamard basis before. So there you go. Already learned something new. So now we have another simple coding example, which is going to be the focus. X gate is to initialize. I just start in state X and 0. Okay, so we either have a 0 or 1. So we want to say if state is 1, then we want to do the X gate on the qubit. Otherwise, we do nothing, so we don't need to do anything. We don't need an else clause to that function. Okay, just making sure it's recording, and we can apply the unitary gate to the appropriate wires. And it is not right. Okay. Let's see. If 1 prepare to state 1. All right, now I don't know what the problem is. Your resulting output doesn't look quite right. Okay, well, let me just see. Maybe I'm doing X wrong. State is int. All right, I do not understand why this is wrong. I feel like I'm missing something trivial here. State. Let me look. Maybe I'm messing up. Sometimes I forget how they do the wires in Penny Lane. So let me check some previous code. No, qubit unitary. Sure, I'll go over here and yeah, that's the same code. Oh, maybe. No, I do not know what is going on right here. Let me double check the problem. Oh my God. What is the difference between poly X and X? I found it. It says complete. Okay, so this is a lesson to always read the problem. Complete the function below using the poly X gate. I do not know. Let me go to any quantum. I do not know. Assuming the X gate is a legal operation. Let's see what happens if I do an illegal operation. Yeah, so X gate exists. I wonder what the difference is. What's the difference between the poly X gate and the X gate? Because X is not right. So let's see, documentation, QML. Poly, I can't spell poly X. All right, somewhere down here should be X. U the position quadrature observe. Oh, it's for continuous variable work. I see. Okay, well, today we learned that this poly x, not x, is it's not very not very nice that it's poly x instead of just x, but that's okay. There we go, correct. So we've been using that a lot. Do I really have to type out Hadamard every time? Let me just see if H. Oh, really? You can, sometimes, like, I think Circ does this where, like, you can type out, I don't know, Fredkin gate or Tafali gate or whatever, but then I think it's aliased is the term, to other, right? You can do CC not, and that's the same function. So it'd be nice if there's, like, if I could just do .h instead of .Hadamard. That is very inconvenient. Hadamard. Especially since I don't know how to spell things, but all we have to do is apply a Hadamard gate. Oh, and return to state. That's all we have to do. Oh, and specify our wires, which I always forget to do. Oh, we don't want that. There we go. Combining your to both 0 and 1. Okay, so what we want to do is just combine them. So if state equals 1, we want to do a poly x gate on the qubit, then apply the Hadamard gate, then apply, just return the U gate. For those of you who are interested, I'll just say this ahead of time, is that we can know that the output of this will be in the z basis state 0 plus or minus 1. If we're mapping the state 0 to the state plus, it'll be 0 plus 1. Hence, probably, I don't actually know if this is true. Hence, where the plus, right? If I go over here, the plus state, where the plus comes from. And that makes sense, right? Because we're not changing the state. So if 0 and 1 are orthogonal in the z basis. So if we're changing the basis, they still should be, like, if it's the same description, they should still be orthogonal. So that's just what's going on here. So if we look, you can see this is square root of 2, square root of 2, square root of 2, or 1 over the square root of 2, and then this is negative square root of 2. Okay, yes, that is what we saw. All right, yes, this is exactly what we said. Now compute this, then write a Q node from scratch. Ooh, you got to remember the function decorator. I'm just going to copy this every time. We specified the device, okay. So we want to define, apply, x, state, I guess. Yeah. So then we do if state 1, qml dot poly x, wires equals 0. Otherwise, we do qml dot Hadamard 0, wires equals 0. qml dot poly x, wires equals 0. And qml dot Hadamard equals 0. And we return the state. And this is Hadamard x Hadamard. In fact, for those of you interested, let's see, let's put my knowledge on the spot. I'm pretty sure this is equivalent to the z operation. So let's see if I can cheat them. No, no, I cannot. I thought I was just going to evaluate the output and realize that it was correct. Oh, I misspelled Hadamard. Because if we think about it, right, this puts it in the x basis. This swaps it. So this swaps the sign of these. So if we swap the sign of these, 0 gets mapped. So if it was 1, right, it gets mapped to this. We swap the sign. So this becomes negative plus. We take, oh, maybe it is just no gate. Okay, now I'm confusing myself. Let me see. Let me think about this for a second. I don't actually know if it's Z now. Now I'm doubting myself. So if you apply the Hadamard to, we get this, to the 1 state, we get this. We apply an X gate to this. We swap the sign of them. In this case, it does nothing. In this case, oh yeah, so it would do nothing, which makes sense. Okay, I was mistaken. Which makes sense. Actually, no, I was right. Which makes sense because this would do no operation, right? Because this is in the X basis, so doing the X operation in the X basis does, in the one of the basis states, I should say, does nothing. Just like the Z operation would do nothing in the Z basis, right? If I have state 1 and I do poly Z on it, nothing would happen. Just like if it was in the 0 state. So I was right. This is equivalent to poly Z in this case, because this will have no effect, because it converts it to the X basis, does the X operation, but it doesn't matter because it's in the X basis, and then returns it to the Z basis. All right, let me check the time, 11:45. All right, moving on. It's just a phase. All right, I suspect we will be getting into phase gates. Oh, look, right here. Hadamard polyx Hadamard has the following effect, which is the exact Z gate. So I was right. Would you look at that? I mean, we already concluded that, but let's see. Global and relative phases. This is something I was actually going to mention, and I sort of mentioned in the phase kickback discussion, but I was going to mention more when it got to like quantum phase estimation and stuff. But basically, global phases, no one ever cares about them. You just factor them out, right? Like this is equivalent to the 1 equals -1. Like that's just a statement. Because it's a global phase, you can factor it out and no one cares. But if it's a local phase, like 0 plus 1 does not equal 0 minus 1. So they call it relative, but it's usually called local phase. So we have a Z gate, or I guess an arbitrary Z rotation here. And it's equivalent to this because you can factor out basically a global phase. If you see, you can factor this out. Worth noting that this is not the case. It's not equivalent. This is what's called like the traditional phase gate or something, P gate. It's not equivalent in every case because there is this global phase. So if you're doing a controlled operation, right, this global phase becomes a local phase. But that's something that will get discussed more when we talk about the quantum Fourier transform. There's also S and T gates, which change phases. Does not tell us what they, oh, here it is. Yeah, so if the omega, or the phase change is pi over 2, this is the S gate. It's pi over 4, this is the T gate. I don't really know why they're called S and T, but those are probably going to be implemented. All right. So now we want to create the plus state, which we do by doing the poly X first qubit, then we do a Hadamard on the second, or on the first qubit, then wait, it said plus state, I'm blind. Then we apply to poly Z, UML.poly Z, wires 0, return state. All right, that should be correct. There we go. All right, now we have a rotation angle. So what do? Use the RZ to do the same thing. Okay. So we just do See, this is why I don't, why it should be just Z, right? If it's RZ, it should be like, I don't know, poly RZ or something, but what do we want? Okay, so it's angle. Is numpy imported? If I'm doing like pi, right? Let's just see. I guess we'll find out. Yeah, numpy is imported. And so we're just doing a pi rotation because if you think about, right, the block sphere as the unit circle, then we want to go halfway around it from the top to the bottom. Or any sort of direction. And so a pi rotation will do that. All right, we can do an adjoint. Also, let's see. Yeah, which is the same as a conjugate transpose. So that's where we swap the rows and columns and make any of the complex values their complex conjugates. So we want to implement the circuit here. So all we do is we have the Hadamard. We have the S gate. I assume it's just S. Let me see if they specify. Yes, QML.S. Dividers by 0, QML.T. Sorry, this is the adjoint of the T gate. Then we have the RZ gate. And then we have the adjoint of the S gate. And then we return state. And that's just the circuit they described there. Should be correct. Oh boy. Let's see. The T gate plays an important role, however, is much more resource intensive to implement in those. Huh. I did not know minimizing T count was something that was of interest. All right, so what we can do here is we can see that we know that unitary matrices, so basically it just says write this gate but optimize it. Okay, I'm not going to implement the original circuit. That's too much work. What we can do though is we can see, okay, those are fine, but we can get rid of some operations by recognizing that a T is a, or a T dagger, they're just rotations in the opposite direction, is a pi over 4 case. So 4 T's in a row is a Z gate right here. So this is a Z gate. 2 T's is a S gate. So what we can see is, let me go down here. I don't want to see if I can see if I can make this so I can see both the circuit. Can't edit this at all. Okay. Well, I guess I'll just get rid of the comment. So what we can do is we can, oh, I know what we can do. We can add things down here. So I can do it this way. All right, sorry, that took a while, but this is what we wanted. So the Hadamards, they are just doing their own thing. So we'll put those in. Do that. And now we can do an S gate on the first qubit, right? Because those 2 T's become an S gate. Do T on the second one. And an adjoint on the third one. There may be a way to combine, let's see, because HZH is a decomposition for X, so maybe HTH is something. I might have to think about that. You could probably express that in like RZ rotations, but we'll see. We'll see if it wants me to do that complex of a decomposition. So then we have another set of Hadamard's. It might want me to do that. I'll have to read the right side if it does. So then we have the, that's not what I want. And then we have the adjoint of S at the top. Then we just have a Z gate, always Z. The second one, and then those are 3. I guess I could write it as an RZ. I feel like that seems like cheating. I feel like I'm supposed to combine it. Like everything, like all the T's could be written in terms of RZs. Like I could replace 100% of them, but that's not really, I feel like, what the desired point is. So like, yes, I could reduce this to an operation of RZ, but I feel like we're supposed to be using non-parameterized gates. Maybe I'm wrong and it'll tell me, no, you need to do this, but let's see. All right, last we have okay, let's see if this is right. Okay, original depth 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, I forgot the Hadamard's at the end. Let's copy this. So the original depth 1, 2, 3, 4, 5, 6, 7, 8, 9. Original T count. Why is this just making me count numbers? Original T count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13. Original T depth. I assume it's just 1, 2, 3, 4, 5, 6. Right? Now, optimal depth is 1. These happen simultaneously. Or let me just think about it up here. 1, 2, 3, 4, 5, 6. 6. Because these combine, so we lose 1. These combine, so we lose 1. So it's 1, 2, 3, 4, 5, 6. Because these will combine and be gone. It'll just be this and that operation. All right, optimal T count. So we can do it this way. 1, 2, 3. Optimal T depth. Let's see. This one, these two are at the same time, so it's going to be 2. Don't know if this is actually going to be right. Wrong. Oh. Oh, wait. Error. Hadamard, wrong number of wires. Can you not do... Can you not do multiple... You can only do 1 wire at a time? Really? That doesn't seem right. That seems crazy. No way. Let's look at the input. Parameters. Sequence of integers. Yeah. No way. This definitely has to be able to take in a... That's crazy. Let me see if it works better this way. That'd be crazy if I have to do it this way. I feel like something else is going on. I'm making some typo or something. But let me just try this first. There's only 3 Hadamard's, so I do not need to save it. I will replace them each with this. Okay, that fixed it, which is very annoying that it made me do that. But now we can see another problem. Original depth of the circuit is not 9. Okay, today we see if I know how to count. 1, okay, let's see, my mouse is visible, right? I think so, yes. All right, so we have the Hadamard layer 1, the T layer 2. We have this T3, this Hadamard 4, this T5, this T6, this T7, this T8, this Hadamard 9. Okay, how is the original depth not 9? How are they counting this? Let me actually read it. The T-gate is much more resource intensive. That's an awful lot of T-gates. Okay, this is crazy. Yeah, that hint makes sense. Okay, maybe it's somehow not counting single layers. Okay, the original depth is definitely TT. No, how is the original depth 8? It doesn't make sense. 1, 2, 3, 4, 5, 6, 7, 8, 9. Unless I'm just really bad at counting. That does not make sense to me. But I'm surprised everything else was right on the first attempt. All right. 1, 2, 3, 4, 5, 6. Yeah. See, they count 1 T dagger there. That doesn't make sense. All right, let me see how long this is. 27 minutes. All right. We will call it here. Next time, I believe, is rotation gates. So just RX, RY. But that's going to be all for now.